Hello, everyone, and welcome to today's webinar, Practical Considerations for a Volume Verification Process for Automated Liquid Handlers. My name is Travis Scherset. I am the Digital Marketing Manager at Artel, and I'll be your moderator for today's event. Before we start, I'd like to go over a few housekeeping items with you. The presentation will last about 30 to 35 minutes, followed by a Q&A session. If you have any questions for the presenters, send them in at any point during the presentation. You don't need to wait until the end. All you have to do is type your question in the chat or question box. I will be monitoring both throughout the webinar. All attendees will be muted during the presentation to avoid background noise and to make sure that you can hear the speaker clearly. In the handout section, you will find some useful resources such as the presentation slides and the scientific poster, Troubleshooting Automation. Lastly, this webinar will be recorded and available on demand on the Artel website. We will also email you a link to the recording within 2 business days. Before we start, I'd like to introduce you to our speakers. John Darren is a global account manager with Artel. His focus is on assisting customers and laboratories with optimizing their liquid handling operations and meeting their productivity goals. Prior to joining Artel, John was a senior scientist at Janssen. For 20 years, he spent his time automating manual processes and developing sample preparation and assay methods utilizing a variety of liquid handlers and automated platforms. Also joining us is Dr. Keith Albert. Dr. Albert is a senior application scientist at Artel and is responsible for automated liquid delivery system performance research, customer education and assay development, as well as method validation services. He has spent nearly 15 years managing and working on various Artel service teams. Dana Campbell will also be joining us. Dana is also a senior application scientist at Artel and is responsible for a successful delivery of a wide variety of field support and training initiatives. He uses his extensive background in pipetting and automated liquid handling to help laboratories build upon their quality focus and relate to how Artel products and solutions help. With that, I'd like to hand it over to John Darren. John?
Thanks, Travis. Okay. Sorry, it's not advancing. So there we go. So today's agenda, we'll start with the risk factors associated with both your equipment and your process when you're developing a verification protocol. We'll talk about the details to consider for your routine verifications. And then we're going to cover some examples of a biopharma R&D organization and how they verify, as well as how a CRO verifies. After that, we can address any questions. So the goals of this webinar are to help you track the performance of your automated liquid handler by covering the importance of a standardized measurement method, the importance of practical routine verification, to cover those examples of how biopharm R&D has implemented routine verification, as well as how a CRO has implemented verification. To start, I'd like to introduce some methods of measurement, as we'll be looking at the Artel method when we cover the routine verifications. So the 4 major methods of verification that folks use are gravimetry, fluorometry, single dye photometry, and the ratiometric photometry found in Artel's MVS. Gravimetry has good accuracy at high volumes, and balances are usually readily available. And there's also traceability via the weight sets. But some of the weaknesses with balances are they're problematic at low volumes. And for multi-channel verification, it can be difficult and time-consuming to complete the verification. So balances tend not to be the best method to verify automation. Fluorometry has good precision and is capable of very low volume measurement, but it has limited accuracy, poor traceability, and it's light sensitive. Single dye photometry has good precision and is insensitive to light, or somewhat insensitive to light, but it also has limited accuracy unless you're making a standard curve, and poor traceability, because even if you do make it a standard curve, you're required to it's very difficult to make that traceable back to another day or another time period you did the measurement. With ratiometric photometry, you get good accuracy at all volumes and good precision at all volumes across the range. It's insensitive to the environment. It's easy to do multi-channels. It's easy to use in general, and it's compliant with regulatory and ISO. I think the major feature, though, is the traceability facilitated by the dual dye approach. It does require an accurate photometer, and it requires accurate and characterized reagents. So the desirable features of a verification system are to be able to measure precision and accuracy, to use application-specific liquids whenever possible, to quickly and easily test the performance when you're optimizing or verifying, the ability to test a wide range of volumes, and most importantly, in order to have good routine verifications, it's important to be able to trace to international standards. A standardized approach to measuring liquid handler performance will allow you to compare things over time or over different instruments or different sites. So that's the question, what do you want to compare? Do you want to compare the same automated liquid handler's performance across multiple dates, which is what we'll be looking at here? Do you want to compare a volume dispensed with the same tip on the same ALH with a liquid class or liquid class variable adjusted? Do you want to compare two of the same brand and model ALHs and see how close they are or how different they are? Or compare two different pieces of automation, or compare a group of manual operators to a group of automated systems? You know, any type of comparison you want to do requires a standardized method. Otherwise, the results aren't comparable. Now I'd like to talk about the installation and optimization process. We'll cover that briefly, but that process will always occur before routine verification. So we'll start by talking about ALH release testing. And ALH release testing can be encompassed by factory acceptance tests, site acceptance tests, installation qualifications, operational qualifications, calibrations, validations. There's so many terms that different folks use for these, but we'll start with the calibration. That's going to include basic hardware tests like tests of stepper motors, pipette mechanics, pumps, grippers, etc. And it will typically be a limited pipette verification, probably with an aqueous solution, and it'll test a low and a high volume of the system. They may do a mid-range test as well, but it's a very basic check just to ensure the system's operating as expected with a predictable liquid, such as an aqueous solution. After that's complete, you'll do an application or performance qualification. And in that, you want to consider your specific workflow parameters, the liquids you'll be using, volumes, tip types, dispense conditions, whether it's a wet or dry dispense, and mixing parameters. So in that phase, there'll often be a liquid class optimization. And what a liquid class is a set of instructions for the pipette to use when it encounters a specific type of liquid at a given volume range using a certain tip size. Those instructions control how the pipette mechanisms behave at a detailed level, and they can be modified to achieve an optimized liquid transfer. Here in the orange, we see the results of a default liquid class when we're seeking 5 microliters. In the green, we'll see the results of an optimized liquid class. So at first, you can see for accuracy testing, the system pipetted 3.7 microliters when the requested volume was 5 microliters. So that's 25% below where it should be. After optimization through those liquid class settings, the technician was able to achieve almost 5 microliters on the nose. And that's the goal in these optimization phases, based on the work you're doing. How accurate you'll need to be will always depend on the work you're doing, but the goal in optimization is to take those default liquid classes and get them pipetting more accurately for your purposes. Next, we see the CV. So by default, the system was pipetting 10.5% coefficient of variation for 5 microliters. So obviously that's a little bit high, and after some liquid class adjustments, they were able to get below 1% CV. And I want to emphasize, although we show here the accuracy results first, followed by the coefficient of variation results, you would typically in process optimize for the CV first and then change settings to address accuracy. And once that's done, you can go ahead and begin using the system. But now I want to get into the routine verification process and some of the risk factors that'll contribute to how you verify routinely. So overall, your quality management plan should include routine performance verification kind of as the mainstay of the plan, but there should also be considerations for verifications for scheduled and unscheduled maintenance, for verifications after a collision, anytime the equipment is moved, ad hoc verifications if a scientist has some questions, or if there's any performance issues in assay. And also you want to be able to verify for new conditions, liquid types or tips, especially during the pandemic when there was a tip shortage. Folks would have to go from their preferred vendor tips to maybe an off-brand tip, and you want to be able to verify that quickly. Having a routine verification plan will help you just put in the new tip and see how it compares to previous data. So when you're building that routine verification plan, you want to think about volumes, liquids, and tip types you're going to use on your system. The system may have a very wide range of volumes available. You may only need to test a smaller range because that's what your process uses. You want to think about the replicates you're going to test per volume and how often you'll test. And some things that may influence this are, of course, regulatory agency requirements. You want to think about vendor recommendations, and you also want to consider ISO guidance. So I'd like to talk a little bit about the ISO guidance. There are voluntary consensus standards. And in ISO 23783, which is coming out, I believe, this month, they've got some recommendations for automated liquid handlers. Again, these are voluntary, but they provide a great base from which to build your own quality management program because they are internationally accepted standards. So for test methods, ISO allows 8 different methods, including the dual dye ratiometric photometry used by the Artel MVS. When it comes to frequency, ISO suggests that you consider the user requirements and the manufacturer's suggestions. In other words, it's risk-based. In terms of the channels you should verify, ISO recommends you verify each channel. And for the volumes to be tested, they want 2 volumes minimum, a low and a high volume of the usable range, as well as if you're going to claim linearity over the tested range, you would need a low, middle, and high. For replicates per volume setting, what ISO considers a calibration should have a minimum of 10 replicates. And what they consider a routine verification or a routine test would have a minimum of 4 replicates. When it comes to volumes, liquids, and tip types, you want to choose a range of volumes that makes sense for your process. Verify at least the lowest and highest volumes used on your ALH. And again, ISO recommends a mid-volume be used if linearity is going to be claimed across the range. You may also choose volumes that occur at a very high percentage in your workflow or are involved in very critical steps. When it comes to liquids, Whenever possible, if you can verify liquids with properties similar to those used in your process, it's just going to provide stronger evidence that your system is fit for purpose. So using those liquids is critical for optimization, and it can be optional for routine tests depending on how you're testing. Artel offers an aqueous solution, a DMSO solution, a serum similar, as well as a PCR mix or master mix similar. And in the future, we'll be launching a plasma similar. Those can really help during that optimization phase, but they can also be used in routine verification. In terms of tip types, you want to test the tips used by your process. Although you may be checking one channel at a time or looking for the results for one channel, that channel may use several different tip sizes. So say a 1 mil channel may have a 10 microliter tip, a 50, a 300, and a 1 mil. If you don't use the 10 or the 1 mil, your routine verification can include just the 50 and the 300. So for replicates per volume and test frequency, you want to remember that routine testing does not need to be as exhaustive as the ALH release testing conducted before the system is put into use. Rather, the routine test is meant to connect back to these data, showing the system is stable and performance is not changing over time. You want to show the system is behaving as expected. For replicates, you want to consider what the vendor recommends and consider the ISO guidelines. So 4 replicates minimum for a routine verification, but you can always do more than that. 5 or 6 is a fine number for routine verification. And always keep in mind any mandatory regulatory requirements. When it comes to test frequency, there's sort of 2 ways to look at this. The first question is, how robust is your ALH? They are typically pretty robust and hold their performance over time. But if an ALH is new to you in your lab, you may want to test how, or at least demonstrate how robust it is, depending on who will be reviewing your work. So a phased approach may help you identify how often to verify an ALH. For example, you could verify daily for 2 weeks. You could verify weekly for 2 months, and then verify monthly for a quarter. A look at that data over time should provide evidence that your liquid handler's performance does not drift. Testing such as this can even begin with data acquired at the factory acceptance stage or any phase of the release testing or calibration. So the idea here is to just demonstrate that over time, as long as things are the same, you're running the same test, the system's performance doesn't drift. If it does, you may want to talk to the vendor because it really should be holding its performance over time, provided there's been no hardware changes or other updates. Next, and probably more important when determining frequency, are the risk factors of your process. So you want to think about how many samples or assays are run between your ALH verifications. Maybe you're only in research, you're not regulated, but you run 100,000 samples a day. How many days do you want to go without checking your instrument? And what happens if you find an issue during an ALH verification? Is the data you've been generating since the last verification in jeopardy? Will you need to do rework? How well does your ALH represent applications you run on them? The liquid type, the volume, tip, etc. If you verify every 6 months with a 10 microliter tip and a 1 mil tip, but you're running a lot of samples every day using a 50 microliter tip and a 300 microliter tip, your verification doesn't quite represent what you're actually doing, and you may want to think about that. You also want to think about how quickly can you find verification reports when they're needed for review, for compliance or regulatory purposes. Also like to take a minute to talk about quality management and manual pipetting. Most assays or processes are developed manually before being transferred to automation. So you want to consider, is there a standardized approach to how new and existing hires are trained to pipette? How often are pipette operators assessed? Are staff trained to pipette the liquids they'll be working with? And how easily can manual operator performance be compared to ALH performance? So if you're implementing routine verification on your automation, do you have any sort of routine check on the performance of the manual operators? And don't be afraid to ask for help. A qualified third party can be a valuable resource for implementing automation. So a good pipette quality management plan should include the following components: assessing the right ALH for your workflow, liquid class development and optimization, the routine and non-routine ALH performance verification, assay-specific pipette performance verification, and manual pipette operator training and assessment. So Artel offers a standardized approach to teach, assess, and report pipette performance across multiple sites, whether you have manual operators, automated platforms, or both. We'll now look at a few examples of ALH verification programs that have been implemented at labs that we serve in the biopharmaceutical industry, as well as a contract research organization. So I'll turn it over to Keith Albert now.
Great, thank you. Thank you, everybody, for being here. My part in this webinar is to give some examples about how an R&D laboratory has implemented a routine verification process for their families of liquid handlers. So an R&D pharma group, their goals, they are set up with a large population of liquid handlers, more than 35. They set out to have tolerances for all the robot transfers for volumes at 10% for both relative accuracy and CV. And regardless of the tolerances employed, the performance of those volume transfers is understood on a robot by robot basis. This particular site is not influenced by regulatory or compliance driven, such as ISO. It is routine testing. It's an interesting example to show with all the guidelines that are out there. They do what's right for their lab, and I think that's important to do something that's to have a volume measurement process in place that works and it's suitable for your environment. So there is routine testing. There's frequent review of the testing results, which is communicated to all the parties, including the owners and the users of the equipment. And after, and during, and before the next service, if methods need adjusting, the robot owners are communicated with, and those changes are either made on site at that moment for ad hoc retesting or for future scheduled testing as well. So why? So R&D pharma, why do they care so much about their liquid handling quality control with their volume transfers? They are a more proactive testing kind of group. Testing is important. This came from the director at the time many years ago. They wanted the scientists to focus on their work and not the liquid handler quote unquote baggage. This department wanted to see transfer issues ahead of time and be aware of ongoing performance trends. And John spoke a little bit about frequency, replicates, and that sort of thing. And this is a different angle approach. The frequency of this group's testing is based on the priority of call it a robot hierarchy. The most important robots, the ones that plate the compounds, DMSO plating compounds, were deemed the most important. So this most important robot group is tested every 2 to 3 weeks, where the less important, the least important, if you will, get tested every 6 to 8 weeks. So every robot in this department is tested within a 2-month time period. So the second on the E, let's talk about the what. So the most important liquid handlers are tested a little bit more closer to how they are used. So more of the method testing versus the robot testing. And these consisted of 8-channel Hamilton stars that dispense DMSO transfers into both 96 well and 3D4 well plates. You could see the target volumes there, 5, 10, 25, 45. And again, that's just 3 replicates per target volume in the 9612 plate. That's deemed necessary enough for this group. And again, with the frequency of testing, which was every 2 weeks, they have a good feel for those trending and those performance issues over time. In the 384 well plate, 5 and 10 microliters with 6 columns each, 5 or 6 columns each. Likewise for the echoes, there are many echoes. 2 different source plates are used, and each source plate holds a DMSO dye and an aqueous dye. So 4 source plates are used to test target volumes of 30, 100, and 200 nanoliters. And every echo that they have equates to 4 destination or 4 test plates per echo. Let's continue here with the less important robots. These robots are tested in a general way as general use performance, but they still cover the important target volumes and the tip types that are used in the general lab work. So some of these just examples, I'm not going to go through the full bulleted list, but they're families of robots. All the 384 tip Bravos are tested the same way with specific tip sizes and target volumes, either in aqueous or DMSO. Likewise, all the 96 tip Bravos are all tested the same way, and so forth down the list. So Biomex, Bioraptors, EvoStars, these were just deemed the less important robots, but less important as the robots who are plating compounds for the group. So I'm going to talk a little bit about examples of the echo testing, the lab site echo testing, now Beckman Echo. Here's a snapshot of a poster that Artel and LabSite collaborated on years ago, just showing that these are the sorts of technical content pieces that are on our website you can download. And it's just showing how the testing with the echo was done alongside the Artel MVS. So the way the workflow works for testing the echo, the source plate is filled with either the aqueous or DMSO dye. That source plate is spun and then loaded into the echo, and subsequently following the test plate is loaded. After the echo runs through its plate reformatter method, it's the plate mate. A plate mate is used to dispense diluent to all wells in the plate. We spin that plate, and then that test plate is shaken and read with the Artel MVS reader. And within minutes, so if the echo takes 2 to 3 minutes to perform a plate transfer, this whole test process is about 5 minutes. With the MVS, 2-minute shake, about a 2-minute read, and the communication that happens is on a weekly basis as soon as the robot performance is complete. Interesting, at least about the echo, you can't really make the user, the owner, the users can't really make adjustments. So the data is what it is. So more with the echo family, service tags are initiated as opposed to adjustments to any of the internal software parameters. Here's a snapshot of an Echo 555 with DMSO and the low dead volume source plate, just to give you an idea of the typical performance that we'll see with the 3 years timestamp, February 16, 17, and 18. And I usually look at the CV values first. So it looks like all the CV values for each timestamp under 2%. Great. This is typical data that we see. And then my eyes migrate towards the accuracy values. Again, very common. And what John was saying earlier, you get an idea of robot performance. And what's not shown here is this particular robot getting tested every 2 to 3 weeks for those 3 years. So I just took the annual snapshot. John, next. Sometimes the testing doesn't go as planned. The data does not look as good as that 3-year timestamp from the previous slide. We could see right away the coefficient of variation in the bottom table, a little higher than it was earlier. And in bold, in red font, is over the 10% tolerances that's expected to be within. So the first thing we do is we back up and we retest, which is something that I encourage users out there. Prove that it's not working. In this particular case, we took a source plate, so that LDV plastic labware was taken from the same lot, dye was put into it and the echo was retested, and then a different lot of the LDV source plate was selected. Sometimes what we see randomly is sometimes the echoes don't see these plastics the same way as from plastic to plastic, and I think that's just important to see. This is testing on the same day. Source 1 was tested about an hour before source 2 and source 3. So the source 2 and source 3 really gave us the confidence that that echo was performing where it should be, and something unknowingly was wrong with that source plate in the source 1 data from the first column. So continue here, just going to show you a couple other data slides of things that we have seen at the site. Combi nanoliter testing. This particular setup was used to dispense in a 3D 4-wall plate, either 1 microliter or 10 microliter aqueous, where the dispensing goes every 2 rows. Row A and B represent channel 1, C and D, channel 2, and so forth, where the combi dispenses from left to right. Row A drops down and then fills right to left across row B and so forth. And what we see here on the data is something that's with a heat map. You can see there's a lot of green and red, a little bit of brown, but there's that blue streak where the highlight is the channel 1. Channel 1 is under dispensing. So this is real data that we'd communicate back to the owner, and the owner would decide if there would be an offset through the software adjustment or a channel. Something wasn't right in the line, maybe the liquid wasn't getting through the line as well. So this is part of the starting point for the troubleshooting. So just to give ideas, we can visually see data differently, and your eyes pick up those heat map signatures pretty quickly. Lastly, for the data set here is especially relevant during COVID, right? There was a lot of tips that were non-existent, if you will. Disposable plastic tips were hard to come by for most makes, models of liquid handlers. A lot of different groups out there were trying to find third-party tips, and when they get those third-party tips, they need a way to evaluate them. So this data is shown for a 384 tip Bravo at 1 microliter, and each column is representing a different disposable tip type. So there's a 10 microliter approved tips, which we assume that those are the Agilent Bravo tips. And then there's 10 microliter tips from an alternate vendor. And lastly, in the last column, 30 microliter tips from a second additional vendor. And just highlighting the circle there with the almost 8% CV, where this lab could determine the risk associated with buying tips from a different party. And they could also assess if they could use, even in column B, column B with the 10 microliter tips, if they could continue using these tips from an alternate vendor to get the same or similar responses as they were from the vendor approved tips. So there's a lot of power. If your QC process or method is easy to implement and it's a short amount of time for testing, you can do rapid fire changes, tip types, liquid class adjustments, and so forth, and make an adjustment or use a different tip and see how that difference, that variable change affects the volume transfer performance. So a few things, just the title of this course is practical considerations, and some of these things, at least with as far as the Artel MVS is concerned, in this particular R&D site, I think there's a few things to share that are worth discussing. And I'm all about building testing efficiencies so you can do more with your time and time savings and working through a workflow that can create advantages of testing. So first 2 bullets, start simple, get the process moving and going, ride the bike a little bit, and then build in more complex testing as needed. Don't start out of the gate with such an extremely complicated test scenario, because if it's too often or too complicated or too many robots tested too many ways, it probably won't happen, or it will be less successful. Always start simple, in my opinion. When possible, Use and prepare source plates with dye. Sources can be created, labeled, they can be centrifuged and sealed for use later. Make sure before these black microplates look the same, right? So you put a good marker to use. A silver marker can be your friend. Label before you go to test, label with the robot ID, replicate number, type of liquid, whatever the information is that you need to know when you run this test plate. What was the test scenarios? Different tip type, different blowout volume, aspirate dispense rate changes. Fourth bullet down, when possible, if you can have a dedicated diluent dispenser, is perfect. In the case for the Echo, the diluent is going in after the volume transfer. In the case for the Bravo, at least for the site that we were, the diluent was going in before the volume transfer into the Bravo doing a wet transfer. Fifth bullet down, if possible, a centrifuge available is very helpful, right? When we're doing photometric measurements, bubbles aren't really friendly. You want to get the bubbles out, and then the liquid in the plate. Another advantage, efficiency builders, testing the same types of liquid handlers the same way on the same day. You're going to have the same reservoirs, you're going to source reservoirs, maybe source plates, the same tip types, potentially the same deck layout. It's a real easy flow when you're running through, and if you're testing 7 different types of robots, one test day each month, it does get complicated. Different reservoirs, different source reservoirs, different plate styles, different locations. So if possible, I recommend doing the same test on the same types of liquid handlers if you can on the same day. Second to last bullet, when the robots have been idle, I recommend doing a dry run without liquids. Just exercise the system before you test it. Sometimes this just moving the pistons, moving the XYZ parameters just gets the robot moving a little, so it's not such a test from an idle position. And then lastly, prepare the QC materials as much as possible in advance so the robots are down for the least amount of time. You get your source plates ready, you get your tips ready, your labeled test plates, so when you walk up to the liquid handler, the method is hopefully written, and just load the deck, hitting go, and then collecting and cleaning the deck and leaving how it was found. And that is my time here for this portion of the webinar. And I'd like to introduce my colleague, Dana Campbell, and he'll take you through a few slides here.
All right, thanks, Keith. A lot of good info. All right, so just like Keith, I'm going to give an example of a service that we do to a different type of lab. They're a contract research organization, and we have a handful of these that we provide services to, and they're a little bit different, and I want to kind of go over why that is and what kind of testing we're doing at a lab like this. So some of the goals that a company or a CRO would have, you know, they want to ensure the quality, compliance, and performance assurance. So their quality compliance, you know, that's really high on the bar of why they're testing. These CROs often, you know, have clients and you know, their customers could be a pharmaceutical company or a biotech company. So they get audited a lot, and so showing how these robots, how these liquid handlers perform, why they perform that way is a pretty big deal to them. Another goal they often have, or we often hear, is that having a third party provide this unbiased and NIST traceable volume measurement data is pretty important as well. And it also frees up the scientists' time. So the scientists at these CROs they're typically very busy trying to pump through a lot of data to get things out. Their whole mission is really to help speed up the timeline from when you know, drugs are being manufactured. So having this a third party do this kind of service is pretty good for them. Another thing is they're not at this point, they're not creating methods on the robot. These methods have already been created. So what they're interested in typically is testing the robots, verifying that they're good to go at whatever targets and replicates and tolerances that they deem fit, okay? So the testing, again, the testing is often influenced by regulatory or their own quality guidelines, as well as input from the liquid handler manufacturers. And again, this helps pass their audits and FDA inspections. Once the testing parameters and methods are created, they're not often manipulated, except to adjust for accuracy. So when I go in, or whoever goes in to do this kind of testing, we're there just to really to verify, and if it's something's not right as far as accuracy, we can tweak that, but we're not going to be spending a lot of time at all doing liquid class optimization. So the example CRO that I wanted to go over is one that we do pretty regularly in the field. These folks have over 20 QIAGEN QIAgility systems. And the QIAgility system pictured here, this is what a typical QIAgility looks like. Inside that blue box is one single channel pipetting head. And so it's a very simplistic instrument where we're just dealing with one channel. The manufacturer recommends a PM, which also consists of a head change, every 3,000 pipette counts. So within the software of this instrument, it's keeping track of pipetting counts, and they abide by that manufacturer recommendation because they want these robots to be in its peak performance at all times. So once it hits that 3,000 pipette counts, that system goes down until it's been serviced by the QIAGEN service engineer. And along with that service is where Artel comes in and verifies the instrument at the specific volumes. So basically, we're trailing right after the QIAGEN engineers. And because they have 20 instruments, we're doing this every 2 months. So they've already did the math behind all this and factored in when these systems are going down. And it comes out to about every 2 months that they're getting PM'd. So they're also getting that Artel verification service. And then we do test a range of volumes with tolerances from the manufacturer's specs. So again, the users have the choice of what specifications they can choose. And in this case, these guys are choosing the manufacturer specs, which, isn't always easy to hit in a real lab environment. But so they definitely push the limits for their robots. So this slide here, it's a little busy, but I wanted to highlight the volume, a couple of things here. If you look at the first column, that first block, it has target volumes from 10 microliters to 200, and that's all in a 96 well plate format. These are all wet dispenses. That means these target volumes are going into a plate or wells that already have liquid in them. And as you look across, this is basically showcasing the mean volume that we're getting, the relative inaccuracy. And the first thing, like Keith mentioned, the first thing I usually zero in on is the CV. And the CV spec for all these volumes here is 1%. And so you can see that the CVs for the volumes from 10 to 200 are very good, very impressive actually, all under 1%. And so now I turn my attention to the accuracy, and I want to make sure that they're all filling what their expectations are, which is 5%. And so we're looking at negative 1%. These are all almost sub 1% accuracies. And this is typical of these QIAgilities. We've tested these so many times, different robots. We get a really good sense over time of what to expect. And these are, again, we're testing right after a head change has happened and the engineer installed, has conducted a PM on the instrument. So this is right out of the box, basically. So the next target volumes we look at, and these are in a 384 plate format, are the lower volumes. So stepping back, these QIAgilities do a lot of PCR setup. And so some of the critical volumes, what they're looking at is very critical volumes that are used in their specific assays. And so they do push the limits down to 2 and 5 microliters. And you can see all the way to the right, there is a failure at the 2 microliter mark. And what it's failing at is not the CV, it's very precise. It's just the accuracy is a little bit high. So it doesn't seem like a lot, but 5% at 2 microliters, that means you only have a tenth of a microliter to play with. So if it's over 2.1, then it's going to flag that as a failure. And it's not, in this case, it's not a bad failure because all that has to happen is a software parameter calibration offset. And at the very bottom, once we put that offset in, we rerun the test. And for the 384 plate, we're actually testing 16 data points, 16 repetitions. And so this is a good snapshot of how the performance is at 2 microliters for this test. And so after one single parameter change, the accuracy is dialed in to 1.99, which is beautiful, which is right where we want it. Okay, John. And I think that was it. So I'm going to turn it back to you, John. Thanks.
Okay. Thanks, Dana. Thanks, Keith. So I'm just going to summarize briefly what we want to consider with the routine verification plan and what your priorities should be. So first, the plan should be practical, using the low and high volumes and tip types that are found in your workflow. You may wish to add additional volumes that occur at the highest percentages in your process or that are especially critical to your process. When possible, consider using liquids and conditions with properties similar to the samples and reagents you'll actually work with. Frequency should be based on an understanding of your ALH robustness, as well as the criticality of your process, or as Keith mentioned, the criticality of your equipment. You may have more important robots and less important robots. Those may be checked more frequently. Consider what actions you're going to take if an issue is found in a routine verification. Will you repeat the test to confirm? If an issue is confirmed, what will your corrective actions be? Routine verification is meant to be less exhaustive than a more thorough calibration and just should reveal any drift in your ALH performance. So routine verification is intended to find issues before they lead to poor process execution or assay data. However, in the real world, poor data is often the trigger to perform testing. Having a standardized routine test will help you quickly identify if the problem is due to a change in pipette performance of your equipment or some other factor in your assay. Routine testing is not about perfect precision and accuracy. Rather, routine testing is about characterizing and tracking the performance limits of your ALH as they relate to your process and assay steps. Precision and accuracy acceptance criteria will vary based on need. So you could be using an automated liquid handler to block or coat plates or do sample additions in qualitative assays, and you may want very different results from those than you would from, say, adding capture, detection, master mix, or sample to an assay. At the same time, serial dilutions that require accurate concentrations in quantitative assays may require even more precision and accuracy, as those errors in concentration will propagate down as you pipette. So I'd like to say thanks to everybody for listening, and we're now going to take any questions.
Yeah, thank you, John, Keith, and Dana for this very informative presentation. Like John said, it's now time for our Q&A session. Remember that you can use both the chat and question boxes for your questions. So feel free to go ahead and send those our way. But I think I'm going to start off with how do I know what tolerances my automated liquid handler should meet?
Yeah, I can take that one. So that's a great question. Unfortunately, there's not a real cut and dried answer to that. I think the first thing is to understand what would be tolerated by your process. So what are the overall process tolerances of your assay or your workflow? And that's going to inform how well your precision and accuracy need to be dialed in on your pipette. As you saw, one of Keith's labs actually has kind of wide tolerances for precision and accuracy, while the lab, the CRO that Dana worked with, had very tight tolerances. And that's based really on the applications that are they're performing there. I would say that generally the manufacturer should specify a precision and accuracy target that they can hit, and you just want to consider whether that's how they get those numbers. Do they use aqueous solutions? Do they use the tips that you use? And are they doing this in a certain environmental condition? Are they measuring gravimetrically or some other method? So while you want to consider what the vendor says, you want to understand, for example, manual pipettes, they often have extremely good specs that they quote, and it will take a near perfect environment and perfect operator to get those specs. So you may want to give yourself a little more room around precision and accuracy. In general, a lot of these automated liquid handlers, depending on volume, can easily get, below 2% CV, below 3% inaccuracy. But again, there's so many different liquid handlers. There's the acoustic pipetters, which are going to go extremely low volume. And then there's the more standard air or liquid filled systems, which, may get down to 2 microliters, but you're going to want to consider your application. If you are in a regulated lab doing quantitative assays, you may only want to use that liquid handler for 10 microliters and up, versus sometimes in a research lab where you may be using the same liquid handler for 1 microliter, because your 1 microliter is probably going to have a higher CV and be a little less accurate than your 10 microliter.
Thank you. I got one more question for you. Besides volumes, liquids, and tip type verification, how do you measure or avoid different plate types, 96 well, 384 well, and from different vendors?
Yeah,
I'm not sure I understand the question exactly.
Yeah. So let me see if I can do that again. So besides volumes, liquids, and tip type verification, how do you measure or avoid different plate types and from different vendors? I think they're asking if there's anything besides volume and like tip type verification, if there's any other type of consideration that you need to take consider in between the different plate types, 96 well, 384, and also between different vendors.
Yeah, I think there is some consideration around plate. So when you're measuring using the Artel system, you will use the Artel characterized plates, which will be a flat bottom 96 well plate or 384 well plate. But the data is still applicable in that you're measuring the performance of the ALH. There will be some consideration if you're going into different plates, making sure that your heights are correct. And those things do play a factor in performance, but they can be subject to visual inspection sometimes, and you can just be sure that your tip is dispensing where it should be for your process, whether that's into liquid or just to the side or using tip touch. And I don't know if Keith or Dana want to speak to this, but I would say that the data is still useful using the Artel plate, and that's what gets you the traceability and the consistency in measurement over time. But I do understand that you'd like to measure in your specific plate.
Yeah, the plates that are V bottom, round well, round bottom, have different dimensions, of course. So like John mentions, if there's the programming ability to do a tip touch or a location, vertical location that's more on the side of a curved well, which is different than a flat bottom well. So those variables should be considered. If you're going into liquid, you're dispensing into an environment that liquid is already existing. The plate geometry might not matter as much as it would if it was a dry dispense. So plate type can make a difference for that, if you want to call it the geography of that tip location, the XYZ location in that well when it's transferring the liquid.
All right, thank you. Got another question. It's what is the lowest echo transfer volume your method can validate?
Our system is spec'd to 10 nanoliters. So in a 384 well plate, we can measure 10 nanoliters of an aqueous or DMSO sample with specifications. The user is allowed to try to test lower than that. I think I've comfortably tested 7.5, so three droplets of a 2.5 nanoliter echo, but I wouldn't push it lower than that based on signal to noise.
Yeah,
So,
I'd like to add to that 10 nanoliters in a 384 well plate is NIST traceable. Anything below that, you can try, as Keith mentioned, and I think the system will do it, but it's not NIST traceable. So I think it's how important to you is that NIST traceability.
Thank you. And it looks like we have one more question, which is, based on my risk, I think I need to verify weekly. How exhaustive does that verification need to be?
Yeah, I can take a stab at that. I would say that it shouldn't be intrusive to your process, right? If you want to verify weekly, I think that's great. And you're looking at ISO recommending a minimum of 4 repetitions per channel. I think the MVS will allow as little as few as 3 repetitions per channel. I don't think that's a great number. I would look for more than 3. So, 4 to 6 repetitions per channel. And, you're really looking to demonstrate that the system hasn't changed. So I think if you verify a few volumes and they haven't changed, it's relatively safe to assume the rest of the system hasn't changed. So if you're measuring your 2 microliter and your 20 microliter, that may be all you need to do. If you span several tips, you may want to do a volume at a couple different tips, but I would say try to keep it practical for your purposes. Consider the number of robots you have. If you're just verifying 1, right, that's going to be no problem. If you've got 25, you're really going to want to plan that out and just see who's reviewing your process and what do you want to demonstrate to them with your data. You just want to demonstrate that the system is not changing over time, that everything's working as expected. I think it can be relatively brief in terms of volume and in terms of the replicates. So 4 to 6.
Thank you. And I think we have time just for one final question. And they're wondering, could you discuss the calibration process for liquid samples via flow cytometry if the sample happens to be less than 2 microliters?
I'm not as familiar with flow cytometry. I'd lean on John here or Dana.
Yeah, I guess I would want to know a little bit more about, is this a pipetter, a robot that's you're just testing at 2 microliters? I think we need a little bit more. I guess repeat the question too.
They're saying yes to your question. And to repeat it is, could you discuss the calibration process for liquid samples via flow cytometry if the sample happens to be less than 2 microliters? Okay,
so yeah, some of the first questions we would probably ask would be the plate format type. Obviously with the Artel MVS, we're working in a 96 or 384 well plate. The channel robot that's dispensing into that plate is important. And typically a good question is it, so we can do what we call a wet or a dry dispense. And so typically with volumes that are that low, we would want to dispense that 2 microliters into liquid that's already in the wells. So in this case, if we're using a 96 well plate, our working volume's 200, we would pre-fill the plate with 198 of diluent, and we'd have that action, that 2 microliter dispense, go into those wells that way. And as far as a process, it's that simple. Your target's 2 microliters, and you're dispensing that into the plate that you want to either 96 or 34.
And where I heard the question, I can't talk to the risk if the 2 microliter in flow cytometry is off. That's where I backed up, and I don't know if it's only delivering on 1.5 microliters. What's the risk to the results that come off a flow cytometer? I don't have that kind of background.
Yeah, as a process, the calibration would be the same in terms of what ISO would call a calibration would be a 10 replicate check of that 2 microliter delivery. And if you're referring to optimizing it, if the 2 microliters is out of spec or not performing as you'd like, that would be sort of a longer conversation, but it would involve adjusting things such as the aspirate dispense speeds, some of the pause times, maybe air gaps to get your CV in line. And once that was done, there might be some adjustments to your liquid handler's accuracy settings. Maybe there's a calibration or offset factor. But once CV was where you want it to be, I would then adjust for accuracy to get that 2 microliters.
Thank you. It looks like we're about out of time, so I would like to thank everyone for joining us today. If we didn't get to your questions, or if you have any additional questions, please don't hesitate to reach out to us. I would once again like to thank you all for for attending our webinar today. And I quickly want to remind you that you can download all related materials from the handout section, and that we'll follow up by email in the next couple of days. We really appreciate you taking the time to join us, and please have a great day.
Thank you.
Thanks, everyone.
Thanks.